Okay, so we're here we go. So last time we were talking about Gauss's divergence theorem. Let me just remind you what the broad strokes are that we developed. So we're talking about solid regions such as this and their boundary surface, which will consist of a possibly more than one, but nevertheless surfaces like that. And specifically, the reason we have to talk about this is because, as with all of these theorems that are all kind of ripping off, the same ideas, the word boundary is a loaded word, and now comes with, there's a subtext. The word boundary always means with a specific conventional orientation. So, as previously discussed. So again, no surprise, all of these theorems, get all having basically the same sort of structure and strategy. There is an accumulating quantity that is ultimately what the theorem is about. So in this case, it's boundary flux. That's the accumulating quantity. We drew this picture and talked about how if you look at the whole solid versus if you look at the left half of the solid and the right half of the solid, the sum of the individual boundary fluxes is the same as the whole boundary flux. Or I should say the boundary flux of the whole. Right? So boundary flux accumulates, and I'm going to add here, over solids. Right? So importantly, it is the solid that we are subdividing. Okay. All right. Let's see here. And then the last observation we made, and this is really very repetitious, but as noted in all of our previous examples, whenever you have an accumulating quantity, any sort of accumulating quantity, that feature of accumulation allows you to think of that accumulating quantity as having location within the solid. Right? Because in particular, you can take whatever your solid is, and however your accumulating quantity is defined, you can chop it up into little pieces. Right? Chop it up into a bunch of little pieces, and you can compute the accumulating quantity on each one of these little pieces. We know the whole is the sum of the parts. That's the accumulation feature. And so how much of the whole is in this little small sub-solid? Well, whatever the computation said it was in this little sub-solid. That's where that part of the whole actually is. And when you have that your quantity has location, you can think of it as behaving kind of like mass, because that's how mass behaves. And once you, I like to use the word stuff because it vaguely suggests something kind of like mass, even though it's non-specific. I think it's convenient. Once you have that it's a stuff, then you can talk about its density. So I guess this is, by the way, where we left off last time. And so picking up now at our usual pace. Reminder what regular density is. Regular density, what they mean by density back in high school, is the accumulating quantity called mass that you find in your solid in question per unit volume of the piece of mass of the piece of volume in question. So mass density is mass per unit volume, quantity per unit size, and again an accumulating quantity. Well, all of that still makes sense if you're talking about flux. Again, outward-oriented boundary flux. So you can talk about how much flux there is associated to that little piece of volume. And then you can talk specifically about how much, volume it's taking up. And then you can talk about the flux per unit volume. And again, that is accumulating quantity per unit size. That, too, is density. So we made analogous observations when we were talking about Green's theorem. We talked about circulation density. That was our sort of first take on what does Green's operator really mean? Well, it's circulation density. And so likewise, now that we're interested in flux density is going to be our interpretation of this formula, which is what you can compute if you set it up appropriately, go through and carry out one of these calculations, a bunch of details that I don't think are really a good time investment in a class like this. So we have a formula that tells you flux per unit volume, namely flux density, and of course we recognize this as divergence. That was discussed back in chapter 3, right? And when we discussed it in chapter 3, it was this sort of unknown origin, just as a word and a formula that I just kind of threw out there and made baseless claims about what it's representing. But now you can see where that all comes from. Divergence represents the extent to which a vector field is kind of emanating outward from a point, because it's literally saying how much boundary flux, how much outward-oriented flux is there per unit size. Kind of stands to reason then. Reminder about these notations. Again, back from chapter 3, previously discussed, both pretty popular, especially this del dot notation, very common in physics that I can attest to, and I would imagine also in the Okay. All right. So, now, reminder, when you have one of these densities, my favorite example for the following point is to think about the fundamental theorem of calculus. We all have good intuition for the fundamental theorem of calculus. We all have good intuition for the density in question for the fundamental theorem of calculus. Namely, the derivative is that density, right? And we can draw pictures of it. We can see it. The whole thing is right there on the graph, and it's very sort of intuitively satisfying. The density points to where the stuff in question that you're measuring is actually happening. It just points right to it. So in the same way that the derivative tells you where the function is changing, tells you where the change is coming from, likewise, divergence, aka flux density, tells you where the flux is coming from. It's that analogous, right? So you take divergence, you plug in the two different points that you're interested in, and then you just look at these values and ask which one's the biggest. Okay, well, it looks like that's the bigger value of flux density. So that's where more flux is being created. Between these 2 points, there is more flux being created at B than there is at A. All right. Okay, so we put it all together. Oh, I'm sorry, question. Yeah.
Really quick, so for this being like boundary flux and like trying to compare it to like last chapter, is like the boundary flux from chapter 6 just on like this through an open surface, and this is like more of like a closed surface around a solid?
So it's a dimension thing, not an open-closed thing. So back in chapter 6, we were looking strictly in 2 dimensions, right? And so you can talk about a 2-dimensional region and its boundary curve, not a surface, right? So flux, boundary flux, as we discussed back in chapter 6, was flux through the boundary curve. So it's kind of a 1-dimensional version of flux. So here we have 3-dimensional solids with 2-dimensional boundary surfaces, and so now we're interested in flux through, again, still through the boundary, but it's just that now that boundary is a surface instead of a curve.
Okay, thank you.
Yeah, okay. Anybody else? Okay. All right, so let's put it all together. We have all the pieces, kind of analogous to the pieces that we put together in our previous theorems. We are going to think of boundary flux, outward oriented, of course. Anyway, boundary flux we're going to think of as being our quantity in question. This is what the theorem is about, is boundary flux. We have observed that's an accumulating quantity, so the whole is the sum of the parts. Specifically, it accumulates over the solid. And so it is the solid that I break up into little pieces and say that the whole is the sum of the parts. Okay. And, as we noted, whenever we have an accumulating quantity that you're interested in little pieces of, you can talk about its associated density. Right? And the density is quantity per unit size, in this case flux per unit volume, that being, of course, what you multiply by volume to get flux. Okay. All right. And having put these pieces together like this, notice that we have our nice theorem, and here it is. Flux integral can be computed with a triple integral over the interior of the divergence. So, very powerful result. We're going to see a bunch of applications of this today. There it is. How we doing? Everybody okay? All right. Now, I do want to point out there's an asterisk on this theorem. There's an asterisk on all of the accumulation theorems, you might call it. At different points in the past, I've had a preference to call these either accumulation theorems or density theorems, or sometimes boundary theorems, because they all involve boundaries. So pick your favorite feature and call it what you like. These days, I find myself preferring to call them accumulation theorems. Anyway, as with all of our accumulation theorems, there is an asterisk. And in this case, the asterisk is right there. Gauss's divergence theorem does not tell you how to compute a random flux. It just doesn't. It only tells you, strictly, boundary fluxes. Only if you're looking at a flux through what is in fact a boundary. If you look at the development of the argument that we just made, it was critical that we were talking about boundaries. That's where the accumulation comes from, in fact, ultimately, is the way we set up the convention for orientations on boundaries. So this is only for boundary fluxes. So let's keep that in mind and continue along here now. Here is my first example. We're going to look at the inward-oriented unit sphere as our domain. We have this vector field as our integrand, and we want to compute the flux. Now, we have a brand new theorem that's about computing fluxes. We've been asked now to compute a flux. We kind of naturally want to see if we can, well, let's use Gauss's divergence theorem as our new shiny tool. Surely we can use Gauss's divergence theorem here, but tragically, no, we can't. At least not exactly as this question is phrased. So, reminder, as we just discussed, the divergence theorem only lets you compute fluxes through boundaries. Strictly, importantly, fundamentally, only through boundaries. So before we can go around using this theorem, we have to check, is our surface actually a boundary? And remember, details matter. Orientations are a big deal. It's not just a minus sign. It's not like just a regular old sign error. It's the minus sign is representative of a significant, sophisticated, critical aspect of the material, right? So this is a big deal, and to be more blunt about it, worth a bunch of points, right? So something that's well worth your time. Our surface as given here, unit sphere, which kind of cruises along like this, but inward oriented, which means it's pointing that way. And is this a boundary? No, it is not a boundary. Again, the word boundary, very importantly loaded term. Boundary means oriented according to the convention, which in this case would be outward. So this is not a boundary. Everybody see the problem? Okay, so you can probably guess how we're going to resolve that problem. I'm going to point out that this surface, the exact same underlying surface, still the unit sphere. I'm only coloring sort of one side versus the other just to avoid kind of, blurring, right? But same underlying surface, this time oriented outward, is a boundary. This is the boundary of the ball. No sweat. Everybody good? So, oh yeah. Mm-hmm.
What's the significance of finding the direction if the magnitude is still going to be the same? You're still getting the same amount of stuff, but it's just
right? No, but there's a big difference between let's see here. If I have a net that I'm trying to hold stuff inside of, there's a big difference between a flux outward, in which case I'm losing the stuff inside the net, versus a flux inward, in which case I'm gaining. So, again, there's a temptation to kind of feel like, well, minus signs are little trivialities, but it's a big difference, right? If the if I'm gaining whatever it is that I have in my net, the fish maybe, that's a good thing. If I'm losing them, that's a bad thing. So, yeah. Does that make sense?
Yeah.
Yeah. Right. All right. So, how are we going to deal with the fact that what we're interested in is the green surface, but what's much easier to deal with is the blue surface. The blue surface is much easier to deal with because it's a boundary. Boundary fluxes, we're allowed to use our new shiny tool. So we need to relate these to each other. And of course, this is an easy relationship to observe. The flux that we are actually interested in through the green surface and the flux that's easier to deal with because it's a boundary, namely through the blue surface, are just negatives of each other. Because these two surfaces are identical except for orientation. Is that cool? All right. Okay, so good news. We have fixed the calculation. At this point, this minus sign that I have here in red will account for the fact that I'm actually interested in a different surface. But in terms of what I need to actually chug out here, I just need to compute this blue flux. This blue flux is literally a boundary flux. Right? Because that S minus surface is literally that boundary. Once I realize that I have a boundary, I can cite my brand new theorem, right? Gauss's divergence theorem says boundary flux is a triple integral of divergence over the solid. And it's all little micro details from here. So let me pause before I go on to those details. Is everybody okay down to this point here? Yeah.
So if we had a question like this on an exam, what is expected for us to write?
I mean, I try to be a good example, right? So if you do what I've done here, that's plenty, right? So notice this equation that I've got right here is recognizing the importance of the orientation. This second equation right here is just overtly recognizing that that opposite surface is a boundary. And then here you can see exactly where the divergence theorem comes in. It is true that a lot of students kind of like to take the statement of the question and very first thing they'll write down is this. And it's like, well, there's a lot going on there, right? There's several steps that go into that. I feel like this is insufficient. This doesn't show, there's no indication as to where this minus sign comes from. Why are we talking about a triple integral over solid where there's no solid mentioned in the question? So that would be too little. If you want to do sort of more than enough, then you could show all three of these steps. I could imagine maybe a student going from here directly to there, and then to there. I think that'd be okay. Yeah. Is that satisfying? All right. Okay, so how are we going to compute the triple integral? Well, we need to know the divergence. I claim the divergence is 3 plus x. This is just a matter of looking at the actual vector field. Here's our vector field. Remember the formula for divergence. We take the x partial of the first coordinate, which gives me the 3, and then the y partial of that second coordinate, which gives me the x, and then the z partial of this, which of course doesn't give me anything, right? That's just 0. So there's my divergence. I now have a triple integral, and I deliberately chose this vector field so that this integral would look like this, because by itself, if you were to take just sort of a direct brute force approach to computing this integral, this integrand, it doesn't have any odd symmetries shared by the ball. You can't use the symmetry theorem. It's not a constant, so you can't use geometry. So it's arguably a hard integral, but the slick move, and it's an easy move, but it's also really slick, is to turn this into two separate integrals, one corresponding to each of the terms. The blue integral is 0 by a symmetry argument. The green integral is easy arithmetic using geometry. So I think it's worth noting, right, that sometimes it is very much in your interest to take an integral and break it up into two separate integrals. Sometimes sometimes in terms of difficulty is not an accumulating quantity. The whole is much greater difficulty than the sum of the individual difficulties. Mix my metaphors. Okay, how we doing? Everybody all? Yeah. Mm-hmm.
Why is it 0?
Why is this one 0?
Yeah.
Yeah. So symmetry argument. So this integrand that I have here, x, has an odd symmetry through the YZ plane, which is also a symmetry of the ball, and so 0 by symmetry. Yeah. Good thing to always be on the lookout for. Saves you loads of trouble. Yeah.
Is that a sufficient argument to state that it's 0 by symmetry?
So that's a great question. Per our exam 2 rules, no. You have to per exam 2 rules, you have to show all 5 of those bullet points that I enumerated. For the final exam, I'm going to discuss and negotiate with the other professor, and whatever the results of that conversation will dictate what the rule is on the final. And I'll make sure to be clear about that. There have been times when the conclusion was that this would be fine. Yeah. So we'll see what we come up with. Alrighty. Now I do want to show you one other thing before we go on to the physics examples. There is a dangerous landmine that I want you all to be aware of. I see students step on this landmine every semester. It's always it's very sad. I've already made a big deal out of how this has got to be a boundary, right? So let me show you what you can accidentally do to yourself if you ignore this point, right? If you're sloppy, if you kind of blow that off as some mathematician formality. Let's suppose that you have a question, hypothetically, I don't know, exam or whatever, where you're asked to compute a flux f dot ds, and let's suppose that your surface here is not a boundary. Let's just say, hypothetically, there's lots of different surfaces that aren't boundaries, right? Floating rectangle, not a boundary, right? But most surfaces, in some sense, are not boundaries. Let's suppose also that this vector field, and the following that I'm about to presume here is not rare. Let's suppose that the divergence is 0. So what would you say, or how would you analyze if you had this question here? How would you compute? And again, the green and the blue comments there are, side notes. How would you compute this flux? And here's what a lot of students will write. A lot of students, this is so dangerous. A lot of students will say, integral f dot ds. Now notice they have not indicated a domain here. They're kind of, like we all do it. We're kind of sloppy about the bounds sometimes. If it's understood what it is, why should I have to write it down? Okay. But then not thinking about the domain, they forget that this theorem only works for boundaries, literally boundaries. And they'll say equals triple integral of divergence, namely triple integral of 0, therefore equals 0. And they happily move on to the next question with this as their work. And here's the thing. Almost all of this is garbage nonsense. Because after all, this only works if your domain is a boundary. By assumption, this S is not a boundary of anything. It's not a boundary, so you can't cite Gauss's divergence theorem. But it's worse than that, because if you think about it, if your surface is not a boundary, that means there is, just to say it with different grammar, there is nothing that it is the boundary of, and therefore there is nothing that could even be the domain for the triple integral. So not only are these two integrals not equal, there is no triple integral. at all to be equal to the flux. It's not that they're different, it's that there isn't a triple integral at all. Which means, of course, that everything that follows after that is absolute nonsense. So notice this, because of being sloppy about this one little, seemingly small point, nothing on the page makes any actual sense. It's all garbage. So you see the danger, right? This is very, very dangerous. Again, I see this every year. It always makes me sad. So heads up. I've shown you where the landmine is. Please don't step on it. Is everybody happy with that? Okay. All right, so moving along. Let's talk about physics a little bit. I mean, just a little bit. We're not going to go hardcore into the physics here. This is not a physics course. But there are instances, and I think this is one of them, where physics actually can be useful in math, just for the purpose of providing a physical metaphor. Right? So don't think of this as math helping me solve physics problems, although that will also be true. Think of this as physics allowing me a way to have a sort of an image in my mind of how to think about what's actually going on when you're looking at, let's say, the divergence theorem. Okay, so my first physical metaphor is a light bulb. I like the idea of having this be an LED light bulb because they are much more point-like than like a filament, right? Filaments are long, skinny things, and it's awkward. So LED light bulb, and what do light bulbs do? Well, they generate photons, right? They that flow like a fluid, and so of course photons, obviously, they go outward like that, outward away from the light source, etc. As you get further away. Now, I'm going to first point out that there is something weird about the way I've drawn this vector field. Notice the field vectors farther away from the bulb are shorter than the ones that are closer to the bulb. And yet, photons always move with a constant velocity. So what's up with that? Reasonable question. What's up with this is that we're going to be interested in this question not in volume of light passing through a surface. We're going to be interested in quantity of light passing through a surface. The number of photons, not the volume of photons, right? And so remember back from chapter 3, if your vector field represents velocity, then you get volume per unit time. That's not what we want. It's when the vector field represents density times volume. That's when you get quantity per unit time, and that in this case is what we want. So this vector field represents not velocity, it represents density times velocity, and there's more density of photons when you're closer to the light bulb, and then they spread out the farther you get away. Is that cool? Everybody happy with that? Okay. All right. Okay. That said, I'm also going to point out that photon density is constant over time, that is. We're not collecting photons anywhere. Any photon that goes into a location goes right back out. There's no sort of like collecting, happening at all. So anywhere you look, the photon density never changes. All right, so what is this vector field? How do I understand this vector field here? And there's a few things to say about that. Again, this isn't a physics class, and I'm going to kind of wave my hands at some of these things. But if you were to write down the formula for this vector field, and if you were to compute the divergence, here's what you would get. And specifically, let's look in different places. If you look out here, away from the actual light source, and ask, what's the divergence in this general vicinity? You will get 0. There's no divergence out there. let me try to persuade you why that's actually pretty believable. And in some sense, this kind of has to be 0. Because here's the point. What happens with photons will flow in to that little volume. And what's the very next thing that a photon does when it flows into this little volume? Well, it flows right back out. Right? And so you might say there's just as much outward flux happening on this little sphere as there is inward flux, because they're the exact same photons, just a fraction of a second later. Right? So net, total in other words, 0 flux on the boundary, and therefore 0 flux density, namely divergence. Is that cool? Now, I like to point out that so we're already seeing why this is such a really valuable physical example, because if you had actually written down the formula for this vector field, I mean, you can write it down. I've got it on the next page, but it's not a friendly looking vector field. And computing the divergence of it, which I've done my duty on that. I did mine many years ago, right? And everybody in this class is going to have to do theirs. But it takes a page or page and a half. It's a slog to actually compute that divergence directly, and you will get 0. So what's cool is this algebraic slog, you can intuit just by sort of thinking physically, thinking about what's actually going on there. You can just kind of, it sort of has to be 0. So this physical model does tremendous calculations for us. And that's really nice. Everybody on board with that? Okay. So what about now instead, let's look around this little sphere here, centered around the LED little light bulb. How much flux is there going through this sphere? Well, very importantly, the light source is on the inside of this sphere. It was on the outside of the green sphere. It's on the inside of this purple sphere. What do the photons do that are coming out of the LED? Well, they go outward through this sphere, and they never come back. So that's not what happened on the green. On the green sphere, they went first in, then out, thus making first negative flux, then positive flux, and the negative canceled with the positive. Here it's just positive. So there is a lot of flux through that little small purple sphere, and I emphasize small, right? That little LED at the center of a LED bulb is a teensy weensy itsy bitsy little thing, right? So a very small little sphere. And how many photons are flowing through it? Well, all of them, 100 watts worth, right? Or whatever the bulb equivalent is. So that's why around this general vicinity, the divergence has to be kind of, if you will, it has to be huge. Right? It has to be huge because there's a lot of flux over a little bit of volume, so flux per unit volume is tremendous. Everybody happy? All right. So, reminder. I've made this observation before that densities point to where the stuff is happening, and again, I think it's a pretty easy pitch when we're talking about the fundamental thermocalculus. Where does change happen? Change happens where the derivative is big. Well, of course, it does. That was one of our primary understandings of the derivative. So, the derivative, namely the density. For that application, density tells you where it's happening. Now, I've made the case that things like circulation and outward-oriented boundary flux, that likewise, those densities tell you where it's actually happening. And it's been kind of a geometric, there's a certain amount of trust involved, right, that you've been sort of, okay, Bray's got a weird way of thinking about that, right? But check it out. It really is the case in this example, right? This flux that you see if you look at this outer sphere, this great big outer sphere here, let me highlight this in, let's say, blue on this outer sphere. There's the same amount of flux through this great big blue sphere as there is through this teeny tiny purple sphere. I mean, how many photons go through this blue sphere? All of them. Just like with the purple one, right? So there's a lot of flux happening that we detect on this sphere. Where is it coming from? Is this sphere itself a light source? No, light source is in the middle. The light source, where did the flux come from? It came from where the divergence says it comes from, right? And none of the flux happening out here, none of it comes from just some random point in the interior. There's no light source there, indicated precisely by the fact that the divergence there is 0. Does that make sense to everybody? So this is a physical example where it is literally the case that flux density is pointing directly to where the flux is actually coming from. So I think that's a nice. I find that very satisfying. Hope you might like it as well. All right, next example. Now this one's a little bit different. The main reason I show you this example is that there really are different kinds of fluids that behave in different ways with different sort of fundamental connection to reality. How does it live in reality? So here I want to imagine an actual gas, right? None of this photon. We're trying to imagine photons as being a fluid. This is just literally a gas. My favorite way of thinking about this one is that I've got a big red balloon, and my red balloon is expanding for whatever reason. I mean, maybe I've grabbed onto it in various places and I'm pulling it outward, whatever. And I appeal to your physical intuition. If the balloon's getting bigger, the air on the inside kind of has to be moving along with it because nature abhors a vacuum and all that. As the surface expands, the air inside of it has to expand along with it. So now, of course, it's expanding faster near the edges. The little piece of gas right there at the very, very center, of course, isn't going to move at all. It's pulled equally in both directions. And so you get a vector field that looks kind of like this, which I claim we can model kind of like that. All right. Now, first observation I'll make about this fluid flow compared to this fluid flow. In this one, we are literally creating fluid. The fluid is the photons. The photons are being generated out of nothing by the bulb, right? Bulbs don't come with a finite supply of photons that it shoots out at a fixed rate. The photons are not already in there. It's literally making the photons. So here we are generating fluid, and yet the density of fluid anywhere in our picture is, again, constant. We don't collect photons anywhere. So the fluid is being generated, but the density is constant. It's the exact opposite with this fluid. With this fluid, we've got a certain amount of air inside of our big red balloon, and that's the fluid. We're not making air. And we're not generating any new air. It's the same amount of air throughout the whole process here. So, and then furthermore, now physical appeal, if I've got a fixed amount of air inside of a balloon, and if I'm expanding it, well, that same quantity is being distributed over a larger volume. The density truly is changing, right? So it's a very different physical scenario, and we're going to interpret divergence in a different way as a result. Okay, so let's think now about this purple sphere here, arbitrarily. Right, and I can talk about how much flux there is through that purple sphere, and you can just kind of see it happening. I mean, there's the air. I mean, as my red balloon expands, air is being pulled out of this purple sphere. And so you're going to have a positive amount of flux of the air as it sort of pushes out of that sphere, that purple sphere. And that purple sphere being a boundary, I can write down the divergence theorem, and I can take this formula for our vector field, and I can compute the divergence. And by the way, this is a nice wrong color. Nice exercise to make sure that you can compute divergence. Please confirm for yourselves that you can take this vector field, compute the divergence, make sure you get 3K as your answer. I'll give you a hint on this one. A lot of students do get stumped on this. What's confusing about computing the divergence of this vector field is that this isn't written in coordinates. Our formula for divergence is based on the coordinates. So the first thing you need to do to this vector field is write out the first coordinate, second coordinate, third coordinate. And then when you have that written down, plug and chug divergence formula, and you'll get 3K. Make sure you can do that. If you have any trouble, come talk to me in office hours. We'll flesh it out. Okay, so what does this all mean? How do I interpret divergence here? Why did I delete that? That didn't make any sense. Hang on, I wanted to delete that. Okay, so how do I make sense out of this divergence here? Well, let's think physically about what's happening in this scenario. I have a flux. That flux is representing air leaving out of this purple volume. This purple volume is fixed, same amount of volume, but air is leaving. So mass per unit volume inside of this purple sphere, mass per unit volume is decreasing. Right? Grand total, I'm losing mass, and therefore I'm losing average density throughout this whole sphere. That's what the flux is telling you. Divergence, here it is. Divergence is telling me flux per unit volume. So when I look, let's say, at this point right there, arbitrarily, I take that point right there, it says here that the divergence at that point is 3K. What that means is of the total flux that I'm seeing, of the mass that's being lost, of the density, the overall density inside of the purple sphere that's being lost, 3K is representative of how much of that decreased density is happening near this point. And now, side note, what about at this point right there? There's a different point. Well, notice 3K is a constant. That means at this other point, I have the same rate that I'm losing density. And if you think about it, this all stands to reason, because when you expand a balloon, the density of the air on the inside, it's always uniform throughout the entire thing. And so if the density is decreasing there, it's got to be decreasing there at the same rate. Again, that's just how gases work. Okay, so different interpretation of divergence because it's a different physical scenario. So something to keep in mind. All right, so when you, in your future engineering classes, physics classes, when they're talking about divergence in some context of a fluid flow, you have to think to yourself very carefully, am I talking about this kind of a fluid that's generated but with constant density, or this type of a fluid that is not generated, there's a finite supply, but where the density is the thing that's changing? Okay, and every physical scenario is different. Real quick, and I don't want to get bogged down in this is a total tangent. This, in case it might be helpful at some future point when you're doing something with fluids, there are some fluids that both of the things are changing. And the way you can make sense out of that, here's the way I like to think about it anyway, is that given your region, oh gosh, I didn't want to do that. Sorry, let me try that again. Okay, given your region, whatever your solid region is, to whatever extent fluid's being generated, I claim there's kind of two different things that can happen when fluid is generated inside of your region. And I don't know how to represent generation of fluid, so I'm just going to do it with some arrows. This makes it look like there's a flux coming from out here. That's not my intent. This is just my intention of there is a red fluid that is being generated here in this spot. So, okay, if a fluid is being generated, such as that, one possibility is it can literally flow out, thus creating flux. That's one thing that can happen if you generate fluid. Here's another thing that can happen, totally possible. If you generate fluid flows in. It could just stay there, and now you've got more fluid than you had previously. And that represents a rate of change of quantity. Right, so these are the only two possibilities. If you create fluid, either it leaves and it becomes part of flux, or it doesn't leave and therefore stays and therefore contributes to the rate of change of quantity. So these are the only two possibilities. That gives us then that these two different forms of generation give us this equation. And in general, depending on what kind of a fluid you're talking about, you just need to ask yourself, well, what do I know about this? Like with photons, this was 0. If dm/dt is 0, then flux tells you how fast you're generating your fluid. If you know that nothing's being generated, then flux contributes to a negative rate of change of your quantity. So this one equation kind of encapsulates both of those examples on the previous page. And then you can think about these in terms of per unit volume and per unit volume. This gives you an morally equivalent equation about divergence. And again, a lot of details, a lot of little things to think about, a lot of intuition to develop in this. Again, that's not my point here. My point here is to give you some things to think about in the future if you find yourself facing a weird fluid that is both generated and of non-constant density. Okay, all right. Let's see here. We only have a couple minutes left. Let me get to gravitational fields a little bit. Gravitational fields we've already talked about. This is the formula for a gravitational field from a point mass. You may recall I rewrote it like this because this helped me justify calling this inverse square radial. Right, this magnitude factor there is inverse square, and this unit vector over here points radially outward. So that's the term inverse square radial. Flashback to chapter 3. I hope everybody remembers that. Now, here's what I want to say. The last thought I'm going to leave you with on this is that this formula, this inverse square radial formula for the gravitational field, believe it or not, is exactly what this photon flow field looks like. Oh gosh, hang on, let me try to delete all this. This photon flow field here, this is inverse square radial. So, okay, well, what a nice coincidence. Obviously, photons flow outward. Gravity pulls inward, right? So there's a different direction. That's just a minus sign, though. There's also different units, and so there's different constants. So sure, but other than the constants, in other words, structurally, the important things about the structure of the flow of fluids out of a light bulb versus gravity, structurally identical. So, as y'all know, one of my favorite points about how to think about this kind of stuff is that when things mathematically behave the same, they might not actually be the same, but you can treat them as if they are and you won't get in trouble. Because mathematically, they behave exactly the same. So feel free to mix your metaphors. And so that being the case, now we come into this thinking of this as being gravity, and it's about forces and stuff, right? But because it's structurally just the same as a flow of particles coming out of a point source, physicists like to think about gravity as literally being a flow of emitted particles. And they use the term graviton. That's a mostly fictitious, theoretical, let's say anyway, theoretical particle, the flow of which outward from the source describes the gravitational field perfectly. And this gives us a really convenient, really powerful metaphor in which to think about how gravity works. And using these ideas, we're going to do some outrageous calculations next time. So see y'all later. Have a good one. Good to see you again. If you came in after I did attendance, make sure I mark you down. See you later.